So now that you guys have gotten comfortable with the vocabulary of vectors and the way that vectors work, the next natural step in the progression is vector-valued functions. In other words, functions that are defined by a set of vectors. All right, and so the important thing to remember about this is that they are functions, all right? And so let's take a look at these functions in the box right here, basically defining vector-valued functions, all right? So notice a function of the form r of t, right? And that's got the arrow over it because it is a vector. And notice what we have going on here, right? We've got each of our unit vectors, I and j, right? Horizontal component of the vector and vertical component of the vector, respectively. And each of those components, right, basically has a function assigned to it, right, that when you plug in values for t, you will get numbers, right? And so when you plug in values for t into x, into y, you'll get a number which will generate each of the components of your vector, right? So that's what this means down here when it talks about the component functions and it says x, y, and z are called component functions and are real valued functions of the parameter t, okay? Right, so basically each of the components of your vectors, right, are a set of parametric equations, right? You've got a function x that will generate the horizontal component of your vector and another function y that will generate the vertical component of your vector, right? So what we mean when we say real valued functions of the parameter t, that just means that you get a number, right? So these are numbers. So that's interesting because x, y, and z are scalar quantities, right? Each of those, like x of 2, y of 2, z of 2, these are just numbers. So these are scalar quantities, all right? But when we then attach them to their vector components, I hat and j hat, you get a vector quantity now, okay? So it's a little tough to, keep it all straight, but really they end up being very easy to work with. And so if you have a vector in 2 dimensions, you are going to trace a plane curve, right? And then if you have a vector in 3 dimensions, you will be tracing out a curve in space, okay? So what we're going to do, again, just to get a sense for how these work, all right, is actually trace out a plane curve that is defined by a vector valued function. And you'll start to see how this is different than just tracing a curve. It's subtle, but it's important. So let's see if I can scoot on down here. Okay, all right. Woo. Okay, so here's the function that we are working with. All right, we've got a vector valued function r, and then we have each of its component functions. All right, so in this case, the t squared, right, that's attached to the I hat, right, that would be x of t, right? That is the function attached to your horizontal unit vector, right, that will generate the number that attaches to that unit vector, right? So this right here, the t squared, that's x of t, right? And similarly, this right here, right, the t minus 1 that's attached to j is y of t. I would actually like to make one modification here because technically, if you scroll back up, right, we define r of t as, some function of t times I hat plus some function of t times j hat. And here we have a minus, so I think it just might be easier, honestly, if we rewrite r of t. So let's see, so we'll just rewrite it as r of t equal to, there's our x, I'm going to write I hat, and then plus, and we'll just say 1 minus t j hat. Okay. All right, so really this is going to be our x here, and this is going to be our y. It's just going to make the computations easier. Okay, and so basically what we are going to do, all right, is compute x of t and y of t, all right, for the values of t expressed in the domain. And since the issue of domain has come up, I would like to make a note about domain in general for any sort of vector valued anything. All right, so here the domain has been specified. If the domain has not been specified, you are generally going to be limited by the most restrictive domain that you have in one of your components, okay? So, for example, if, for whatever reason, you had, some vector defined by the natural log of t I hat, and we'll keep it simple, plus t j hat. Well, guess what? There's no restriction on the t component, right? But this is going to be a little bit restricted. So guess what? The entire domain of the entire vector valued function r is going to be the domain of the natural log of t. So basically from 0 to infinity. So you basically take the most restrictive of the domains, or you could almost think about it as the intersection of all of the different component functions and their domains. Okay, so let's just get this out of the way right here. All right, and so basically, since our domain has been specified for us, we only need to consider values of t between 0 and 3. All right, honestly, I put the half increments in here. Now that I'm looking at it, I don't know. I might just do the whole numbers, the integer values for t. But you are welcome to do the ones in between if you feel so inclined. Because really, we just need to get a sense for how this works. And doing the integer values of t, I think it'll be sufficient. We'll see. All right, so basically, we're going to plug each indicated value of t into the component functions, x and y, and that will generate a vector for us. All right, so let's start with t equals 0. All right, so when t is 0, x of t, which is equal to t squared, will be 0, and y of t, which is equal to 1 minus t, will be 1. So that means, all right, that r of 0, right, will be 0 I hat plus 1 j hat. All right, so basically no horizontal component to this vector, just vertical. All right, so now let's go ahead and do the same thing for t equals 1. So when t equals 1, x will be 1 and y will be 0. Oh, okay, so now we have the flip case, right? So when when t is 1, your vector is 1 I hat plus 0 j hat. And then let's see, when t equals 2, x will be 4 and y will be negative 1. So r of 2 is therefore 4 I hat minus 1 j hat. And last but not least, when t is 3, x is 9, y is negative 2. Therefore, our vector valued function, when t equals 3, is the vector 9 I hat minus 2 j hat. And that's fantastic. But what do we do with these points? Well, we draw the vectors. All right, so let's lay these 4 vectors, right, in this rightmost column. Let's draw them. All right, so r of 0. All right, that is no horizontal component, right, and 1 vertical component. So you know what? I'm going to label 1 up here. All right, so that is this vector right there. Fantastic. All right, and then r of 1 is 1 in the horizontal direction and none in the vertical. So you know what? Let's scale this. Okay, and we'll just put in a few numbers to give us some sense of scale. All right, so r of 1 will simply be the horizontal unit vector. Great. All right, r of 2 is 4 in the horizontal direction and down 1 in the vertical direction. Okay, so 4 horizontal, all right, and -1 vertical. So that's going to bring us basically to the point for -1. So here we go. Okay, and then last but not least, r of 3. So you have a horizontal component of 9 and a vertical component of -2. So that's basically the ordered pair, 9, -2. And this is the other reason why I feel like it's good to just do the integer. Okay, let me fix that. Why it's good to just do the integer values for t, because this picture does tend to get a little crowded if I put all the vectors that I have listed here. You could see the picture would get very crowded. So this is interesting, all right, because what we have here are 4 vectors corresponding to r of 0, 1, 2, and 3. That's great. How does this trace out a curve? Well, as you can probably see, right, each of these vectors locates a point on the coordinate plane. r of 0 directs us to this point right here. r of 1 directs us to this point. r of 2 and r of 3. And so when we connect, right, the points that have been located by the different vectors, it traces out a curve, right? And of course, the domain for this vector valued function was all t between 0 and 3. So, t equal to 0.1 is there, t equal to 0.7 is there, t equal, to pi over 2 is there, right? So you do hit every intermediate point in between, but I just picked these 4 to give you a sense of how these work. So really, right, if we think about drawing out all the vectors for all the values of t, what we would have is a collection of points so close to each other that we might as well just draw a curve, right? So basically like this. So that right there, that is our plane curve. Right, but notice that that plane curve, right, the points on it are initially located by vectors. So the curve is just the part in green, but the blue part is the actual work of, tracing out the points that we are supposed to hit along the way. And of course, since this is, a vector-defined function, we have a trajectory, right? So we always want to plot an increasing value of t. So we know that we started at the point 0, 1 and ended at the point 9, -2. So we should just, put an arrow on there to indicate this is the way that we're going. And that's all there is to it. See you on the next page. So on the previous page, we were given vector-valued functions and then used them to generate the graph of a plane curve. Now we're basically going to work in reverse, where we know what the plane curve looks like, right? Because here we've basically eliminated a parameter, right? There's no t involved. It's just y as a function of x. But we might want to, for whatever reason, define this by a vector-valued function. All right? So I always say, if you can, make a picture. So that's exactly what we're going to do. And hey, we know what a parabola looks like, right? So, All right, and let's see, it's y equals x squared plus 1, so we're really not going to need the whole thing. Great. Okay, so x squared plus 1, it's about as easy as it gets. Okay, so that's the plane curve right there. Y equals x squared plus 1. All right, and so now, right, finding a vector valued function basically involves, right, writing out something of this form, right? Since it's a plane curve in 2 dimensions, right, we know that we just need 2 components, right? So in other words, x of t I hat and y of t j hat. So it turns out that writing a vector valued function for a plane curve basically reduces to finding a set of parametric equations for this function right here. And we know how to do that because we did section 10 too, right? It's basically find a set of parametric equations. So one thing that should be sort of maybe going off in your head right now is there could be more than one answer. All right, so for now, we're gonna take the easy one because we can. All right, so let's say, all right, x of t, like, why don't we just let x be t? That's fine, right? So let's say that x is equal to t. Fine. So then that would mean, right, that x of t is just t. Ti, right? And then plus, all right, well, if x is equal to t, then that means that y is equal to, now, t squared plus 1. Okay, so then plus, right, t squared plus 1 j hat. And so that's going to be enough to do it, right? This is the vector valued function that will trace out this plane curve just with a whole bunch of vectors. All right, but what I would like to do is confirm, all right, that this actually works and that our, basically our parameterization of this function creates a vector valued function that does what we want it to do. So we're just going to choose a couple values for t. All right, let's maybe choose, so let's see. We'll do t. We're basically just going to make a little chart like we did before. All right, we'll make a column for our horizontal component, our vertical component, and then just to bring it on home, we'll write out a column for our vector. All right, so, I mean, really the domain of each of the components of our vector, right, the domain of the horizontal component and the domain of the vertical component are all real numbers. So we can pretty much pick whatever we want. But for now, maybe we'll just do, we'll do -2. Yeah, we'll just do these values for t. Okay, so when t is -2, x of t, which is just t, is, well, -2. And then y of t, which is t squared plus 1, would be 5. So that gives us the vector, right? So basically r of -2 will be -2 I hat plus 5 j hat. All right, so to draw that vector, right, that's -2 in the horizontal direction, 5 in the vertical direction. So, maybe we locate that point up here. We'll say that this is 5, this is -2, figure not drawn to scale. And there's our vector right there. Okay? And because of the way that parabolas work, right, they're symmetric, so we might as well just go ahead and do this one right here. Right, but this will just be positive 2i plus 5j. Okay, and so then we'll put a positive 2 over here. That's going to locate this point for us, and we'll draw that vector. Hopefully your parabola is a little bit more symmetric than mine is. Okay, and so when t is -1, x is -1, and y is 2. So our vector at -1 is -1 I hat plus 2 j hat. So here's -1, and then maybe, maybe here-ish is 2. All right, so here is our vector, right? So this vector, right, just to bring it on home here, this is r of -1, right? And again, let's use symmetry to make our life easy here. So that's going to be 1 I hat plus 2 j hat. So here we'll put in the point 1. There's 2, so that's going to be approximately this point right here. Good. And then last but not least, let's do 0. Hopefully you should have a sense of what should happen, right? When t is 0, x is 0, and y is 1. So r of 0 is 0i plus j. So just j hat, which would just be, right, this point right here. Right, so everything should be working, right? And so, again, the vectors are just kind of shooting out from the origin to locate each of the points that you're going to eventually trace. And so let's just go ahead, do this one more time to sort of seal the deal, and hopefully you'll be feeling pretty comfortable with the ideas behind vector-valued functions. Okay. So here we are asked to represent the plane curve, which looks to be a circle, by a vector-valued function. So if we know what this looks like, we should most certainly draw it first. All right, so let's get our coordinate plane. Looks like we have a circle, and that circle is centered at 2, 0. All right, so let's mark this out. Let's see, 1, 2, 3, 4. All right, so this is the center of our circle, and it has a radius of 2. All right, so we'll need to go up 2 and down 2. And then I am going to do the best I can to make an acceptable circle. What you don't see right now is me spinning my iPad in all sorts of crazy directions to make this happen. Okay. Oh, ooh, no, I can't. Gotta fix it. All right. She ain't pretty, but she'll do. All right. Okay, so this is what we're looking at. All right, so again, to find a vector-valued function for this circle, that is simply a matter of defining component functions to attach to each of our little unit vectors. So basically, we need to find a parameterization for the given equation. So, why don't we let this right here be t? Let's see what happens. All right, so let's see what happens if we let x minus 2 equal t. And again, there's a lot of ways that you could do this. You could just be like x is t, or you could say that t is going to be the entire x minus 2 squared. So I encourage you, if you feel so inclined, to go ahead and try that out. All right, but for now, all right, if x minus 2 is t, then that is going to mean that x will be given by t plus 2. So x as a function of t is t plus 2. So at this point in our work, we have this, t plus 2 I hat, and we still need to figure out what is going to be our vertical component function. All right, so let's see. currently, if we look at the function that we have, all right, we had x minus 2 squared plus y squared equals 4. Well, guess what? I called x minus 2 t, so really I have t squared plus y squared equals 4. So now figuring out the appropriate choice for y is just a matter of solving for y so that we get y as a function of t. So, all right, y squared equals 4 minus t, and therefore y equals the square root of 4 minus t. And that should do it. All right, so here, 4 minus t j hat. And you might notice an issue with something. So we'll talk about that in a minute, I promise. All right, but for right now, let's start tracing some things out. All right, just to confirm, that this vector valued function is going to work for us, and also to figure out trajectory, okay, which I realize now that we did not do for example 2, but just knowing that you go in increasing value of t would tell you that you need to put the arrow on the parabola so that you know that you're moving from left to right. Okay? All right. So let's start out. And again, it looks like the domain of each of our component functions, I was going to say, is all real numbers, but that does not seem to be the case. It looks like, based on this piece right here, that our domain is going to be, right, basically we can go up until 4. So from negative infinity to 4, right? Anything greater than 4, and we enter imaginary territory. All right. So, all right, let's just choose some numbers to plug in. All right, so let's see, maybe I'll just do, all right, so t, x of t, y of t, and I'm just going to pluck the vector out from our x and y components. So let's just do like 0, 1, 2, 3, 4. Okay, so when t is 0, x is 2, right? Because x, again, is t plus 2. And y is also 2, right? Because 4 minus 0 is 4, and the square root of 4 is 2. So r of 0 will give us the point 2, 2. So this vector right here, this is r of 0. Okay, r of 1. All right, well, let's see. X will be 3, and this will be root 3. So let's see, 3 root 3. There's r of 1. Okay, and when t is 2, x is 4, and y is root 2. And now that I write this, I realize I made an error in my previous work. It's actually down here. I forgot to square the t, right? Because I'm like, this should be the 0.40, right? I know that, right? So I forgot to square the t. My apologies, right? So now, and this is why it's good to check, right? I checked my parameterization and found an error. Okay, so this is actually 40 now, which brings us right here. Okay, and so now this actually impacts my choices for t as well, because as you can see, I shouldn't really be plugging in t equal to 3 anymore, right? So my domain has changed, right? Now my domain is from negative infinity just to 2. So actually, I don't want to plug in 3 and 4. Oops. Come on, eraser. There we go. All right. And now you might be noticing, all right, an issue with our domain, right? Specifically at this step right here in our solving, right? Because technically we should have had a plus or minus, but how do you put a plus or minus, on a vector valued function, right? Because if you notice, right, if we were to choose t equals, -1, right, for our x component, we would get, when 1, right? Yes, basic arithmetic. And then for our y component, you would get, right, √3. Right, and so what you realize is, based on the way we set this up, we're always going to get out positive numbers, so we are only ever going to trace out, right, half of the circle. So what you might need to do here is define a second vector valued function so that you can trace out the other half of the circle, right, with the negative square root. So that's a consideration, all right? But ultimately, I think that the concepts underlying a vector valued function are not terribly difficult. As with everything that we do, there's minutia that, that we can get bogged down in, and it's tough to, use the proper vocabulary and be technically correct about everything. But I think conceptually, this is not a difficult one to wrap your brain on. And like I've been saying, this basically works the way you want it to work. So yay, congrats. You did vector valued functions. Coming up next, calculus.